Welcome. We are now going to look at the control volume and the forces on that control volume, and we are trying to write balance for all the forces that act on that control volume. Just to tell you where we are in the course, we are on microscopic momentum balances. Quickly revision of the previous lecture. Explain the concept of viscosity from the point of view of molecular motion. Why is it that the molecular motion causes force, momentum transfer, and how is viscosity related to the molecular motion? What is the physical significance of dynamic and kinematic viscosity? Right? What are their units? What is the unit of dynamic viscosity? Mu, or kinematic viscosity? Mu by rho, or called as nu. What is meant by normal and shear stresses? Okay, so revise this, answer this, so that will be a revision of what we have done in the previous lecture. Now we can go to the actually writing the forces on this differential element. So first of all, we are going to write mass balance. So imagine this box again. So x direction, y direction, and z direction. This is delta x, this is delta z, and this is delta y, the size height of that box. Now imagine that Vx is there, Vy is there, and Vz is there. All the three directional forces are there. All the three directional velocities are there. We just write that Vx is there, Vy is there, let me write this properly. Vx is there, there is Vx, there is Vy, and there is Vz. Velocity is there in the x direction, velocity is there in the y direction, velocity is there in the z direction. Some of these could be zero, but in general we are writing. Now here is the thing, what we are going to do is the rate at which mass enters or rate at which mass leaves this control volume. And of course the difference we have seen, mass entering minus leaving, is the accumulation of mass in this control volume. Okay, now if there is a flow rate in the x direction, imagine that you are in a room and you want to go out of that room. You will go out of that room through a door, right? Visualize that you are in a room, you want to go out of that room, so you will go out of that room through a door, and you will go out of the door, you will go out of the room through the door only when you have a velocity in the direction perpendicular to the door. Perpendicular to the door. If you have a velocity in the direction in the same plane as the door, you will just move along the door, either horizontally or you will move along the door vertically. You will be able to, suppose this is the door, you will be able to go through the door only if you have a velocity component perpendicular. So imagine that this box that you see, imagine that each of these sides is a door. So there is the left door, there is a right door, there is a front door, there is a back door, there is a top door, and there is a bottom door. Now material can enter through the left door only by a velocity component Vx. If there is a velocity component Vy, you will just go along the door in the vertical direction. If there is a velocity component Vz, you will just go along the door in the z direction. The only way you will be able to enter this box, only way now the fluid will be able to enter this box, is if it has a velocity perpendicular to the left face door in this particular case, and that is Vx. So the volumetric flow rate would be Vx evaluated at x multiplied by delta y delta z, area of that door, if you like, area of that left face, delta y delta z, multiplied by rho. So rho Vx multiplied by delta y delta z, that is the volumetric flow rate, multiplied by density, that is the mass flow rate through which the fluid will enter through the left face. Let me just rub out these unnecessary things. There are small things that are written. Let me just rub them out. Right. So the volumetric flow rate entering, or mass flow rate entering through this left face, is rho Vx delta y delta z. Similarly, volumetric flow rate leaving the box through the right face is rho Vx, but evaluated at x plus delta x multiplied by delta y delta z. Okay. Same way, Vy, if velocity in the y direction is there, liquid or fluid can enter the box only through the bottom face or the top face. If there is velocity in the z direction, fluid can enter this control volume only through the back face or the front face. Fluid can enter the box because of velocity in the Vx, because of velocity in the x direction Vx, through an area perpendicular to the x-axis. That area perpendicular to the x-axis is delta y delta z. Liquid can and fluid can enter the box, leave the box in the y direction because of Vy through an area which is perpendicular to the y direction, which is delta x delta z, the top face and the bottom face. So Vy delta x delta z is the volumetric flow rate multiplied by rho, that will give you the mass flow rate. Similarly, z direction, front face and the back face, liquid can enter or leave through Vz, because of Vz, through an area perpendicular to the z axis, which is delta x delta y, which is nothing but the front face and the back face. Now let's write all these balances. So again, this is rho Vx delta y delta z, that's what is entering through the left face and the right face, minus rho Vx delta x delta Vx evaluated at x plus delta x, entering, leaving. Same way in the y direction, entering through the bottom face, leaving through the top face. It has an area delta x delta z. Similarly, rho Vz at z, entering, back face, leaving, front face, they have an area delta x delta y. Accumulation of mass in this control volume is nothing but volume multiplied by density. Delta x delta y delta z is the volume multiplied by density, d by dt of that, derivative, time derivative of that. We've seen that in unsteady state balances. That's why we did unsteady state balances, because we have to do this now. Now I can divide throughout by delta x delta y delta z, take limit as delta x delta y delta z tending to 0, all of them tending to 0, convert these differences into a differential. So delta rho by delta t, differential, and remember the derivation, remember the definition of derivative, right? It is f of x at x, f at x plus delta x minus f at x divided by delta x. So this is a negative of the derivative, right? So write that, and we can bring it on the other side. You will get del rho by del t is equal to del by del x of rho Vx, del by del y of rho Vy, del by del z of rho Vz. It is, rather than writing in this x, y, z form, we write it in an easier manner in a vector notation. So if I write velocity vector as Vxi, Vyj, Vzk, and a differential operator delta as del by del xi, del by del y of j, del by del z of k. So this whole thing, this bracket, I can write as a vector, as a dot product of del operator and a rho v, right? It's like a dot product, if you want. This operator and this vector. Operator is a vector, it is in all the three directions, that's why it is an operator. And del rho by del t as it is. Sometimes it is easier rather than writing. Some of you may find that writing in a vector notation like this is not very convenient, or not very what shall we say, not very easy for you. So then we can also write it as like this: del by del xi rho vi, and I is just an indicator, it's just a counter, if you like, of all the three directions x, y and z. We can write it like this as well. I is like a counter, so it is del rho by del t plus del by del x of rho vx, del by del y of rho vy, del by del z of rho vz. You can write it like this as well, right? It is the same, either here you write it like this, or in the vector notation you write it like this. If the fluid is incompressible, means like a liquid we say incompressible. Now the word incompressible means density is not changing significantly, or the density change is negligible with respect to x, y and z, and with respect to time. So if it is negligible with respect to time as well as x, y and z, that means density is not changing. For a gas, density changes. It could change in the x direction, y direction, z direction. If pressure is changing, let's say atmosphere, density was changing in the z direction. Okay. Or it could change with time. I'm compressing a gas. I'm allowing a piston to compress the gas. If the density is changing with respect to time. Liquid is essentially incompressible, because even if you are trying to compress, the change of pressure required to get a density change is very large, and we don't encounter these changes of pressure very often. So even if the pressure changes, density is the same. So rho is independent of x, y and z, and rho is also independent of time. And then if it is independent of time, then we can say that this accumulation is 0, this is 0, and this rho, because it is incompressible, because it is not changing with the direction, I can take this out of the differential, I can take this rho out of the differential, and if I do that, divide throughout by rho, I will get this equation. So this is an equation of mass balance, which is called as equation of continuity. We can write it either as del dot v, del operator dot product with v operator, right? We can also write it like this: del by del xi vi equal to 0. What is the physical meaning of this? It is only telling you if there is a change in Vx in the x direction, it will correspondingly lead to a change in y direction, Vy in y direction, or Vz in z direction. Imagine that imagine one problem that we did. We had a plate and we had a jet of water striking this plate, and then the jet was going like this. So if you think of this as the x direction and this as the y direction, and let me take another color, and if you take this as a control volume, let's say this is our control volume, Vx is 0 near the plate surface. Vx is a very high value away from the plate. Vx is 0 near the plate surface, stagnation point if you like. That means Vx is changing in this control volume. Vx is changing with x. That means this is non-zero. If del Vx by del x is non-zero, either it will lead to del Vy by del y or del Vz by del z, or both. Which means now fluid is going in the y direction. this is Vy. So Vy was 0 here, Vy is some value here. So Vy is changing in the y direction. Vy is changing in the y direction. That is the meaning of this. Whatever is the change in the x direction, velocity change in the x direction, Vx change in x direction, which means the fluid will turn, either it will go in the y direction leading to an increase in velocity in the y direction with respect to y, or an increase in velocity in the z direction with respect to z. Right? Okay, let's go forward. Think about this. Suppose we have a cylindrical coordinate system. Now cylindrical coordinate system means we are going to take along the axis as the z direction, away from the axis, this is the axis, away from the axis is the r direction in all directions, and around the axis is the theta direction. So if this is our control volume, this height, this would be delta z, this distance would be, or this length would be delta r, and this arc around the axis would be delta theta. Okay, now area of this face is dr dz. Area of this face, back face, is dr dz. Area of this top face is r delta theta multiplied by dr. Area of this curved face is r delta theta multiplied by delta z. Okay, try to visualize. So now can we write, now we have velocities in r direction, theta direction and z direction. So if you write accumulation as mass flow rate in minus out, mass flow rate in minus out in the r direction. So liquid or fluid will enter this box in the r direction. Because of only velocity in the r direction, it will enter through an area which is perpendicular to the r direction, which means this curved surface and this curved surface. Okay. Area of this curved surface is r d theta, r delta theta multiplied by delta z. Look at this. It is at r and at r plus delta r, because Vr can change with r. In the theta direction, now fluid can enter this control volume in the theta direction because of velocity in the theta direction through a face which is perpendicular to the theta direction. Perpendicular to the theta direction means this is this front face and this back face. Area of that front face and the back face is dr multiplied by dz. So mass flow rate in and out because of the theta direction is the area perpendicular to the theta direction, which is delta r delta z, the front face and the back face. Fluid can enter because of Vz through a face which is perpendicular to the z direction. Perpendicular to the z direction means the bottom face and the top face, this top face if you see, and the bottom face. Area of that top face and bottom face is r delta theta multiplied by dr, r delta theta multiplied by dr or delta r. Okay. Now accumulation is del by del T of rho multiplied by volume. What is the volume? R delta theta delta r delta z. Again divide throughout by r delta theta delta r delta z. Take limit as delta r delta theta delta z tending to 0, and you will get this equation. Simplify, you get this equation. Get it for yourself. Derive it for yourself. Vector notation. Now we can write the same notation. Only thing is this differential operator will be different in the Cartesian coordinate system, in the cylindrical coordinate system. So Bird-Stuart-Lightfoot's book appendix gives you the values of this operator for different coordinate systems, Cartesian coordinate system, cylindrical coordinate system. Writing in the vector notation is that this equation also we can write as the same. Let's take another color. Yeah, let's take R. So del rho by del T we can still write it as del operator dot rho v is equal to 0. It's like a dot product. Okay. But the del operator is now different for Cartesian coordinate system. It is different for cylindrical coordinate system. So you don't have to derive all this again from a control volume perspective, right? If you just say that this equation once you have derived, this equation once you have derived, this equation once you have derived, and you have written it in the vector form, you just have to write the proper differential operator in the Cartesian coordinate system, cylindrical coordinate system, or spherical coordinate system. That's the advantage of writing in a vector form. Okay, so visualize all this for yourself. Okay, make a box, Cartesian coordinate system, make a box in the cylindrical coordinate system. Cylindrical coordinate system is like a piece of a cake, right? So think about that. Anytime you cut a cake, cut the cake at two different values of theta, you will get a sector, you will get an arc, you will get a piece of cake. Cut it in the z direction, you will get a slice, and cut it in the r direction. That's how this fluid element will look like. That's how this fluid element will look like. That's how this fluid element will look like. Okay. Visualize, try to write, try to imagine where flow is entering, where flow is leaving. Visualize for yourself. Do that for yourself. Once you are clear, then only go forward. This del dot v in mathematical language is called as a divergence of this velocity vector. Divergence. You might have studied in your applied maths courses. Let's go forward. So we have done mass balance. Next step is momentum balance, right? Before that, just to give you equations, appendix B.4 gives you these equations of continuity for incompressible fluids in BSL's book, Bird-Short Lightfoot Transport Phenomena. Okay. You can see the Cartesian coordinate system. It is the same equation, del rho by del t plus del dot rho v, divergence of rho v. It is del by del x rho vx, del by del y rho vy, del by del z rho vz. We have derived this. Same way cylindrical coordinate, we have derived this. Just the del operator is different in Cartesian, cylindrical, and spherical coordinate system. Okay, that's the advantage of writing things in a vector notation. Very compact, generalized for all the coordinate system. Del dot v, divergence of v has to be 0, continuity. Okay. Let's go to force balance now. Little bit more involved we are looking at. Okay, here is that Cartesian coordinate system again. Here is the box, delta x, delta z, delta y. We are only writing first of all force balance in the x direction. Okay, force balance in the x direction. Let's go step by step. Let's look at one line at a time. We are writing force balance in the x direction. Okay, let's write pressure forces. Pressure force in the x direction is going to be in the x direction. Pressure is going to act perpendicular. So pressure force in the x direction is only going to be because of the left face and the right face. So the pressure force is going to be pressure multiplied by area of the left face, delta y, delta z, multiplied by pressure, delta y, delta z. This left face evaluated at x Right phase evaluated at x plus delta x. Pressure we have seen macroscopic balances when we did. The net pressure force is what is difference between what is acting on the two sides. Gravitational force, mass of that box, mass of that control volume, rho multiplied by delta x, delta y, delta z multiplied by g. Now this g I am going to take either 0 if the x direction is horizontal, but we are writing in general. So the x direction we could write, this x direction could be vertical. So then g, if x direction is downward, g would be plus 9.81. If x direction is upward, g would be minus 9.81. So I'm just writing it g, but what I'm really meaning is the component of that g in the x direction. Right? Let's write that. Let's make that correction. Right? Component of that gravity in the x direction. Component of the gravity force in the x direction could be 0 if the x direction is horizontal, could be plus 9.8, could be minus 9.8 if the x direction is vertical. Viscous stresses. Again, we are writing only the stresses in the x direction. Recall from the last lecture, revisit that lecture if you want. Forces in the x direction. Forces in the x direction where sigma xx, tau yx, tau zx. Sigma xx is on the right face, on the left face. Tau yx is on the bottom face and the top face. Tau zx is on the front face and the back face. So sigma xx left face and the right face, area perpendicular to the x-axis, delta y delta z, delta y delta z at x and x plus delta x. Tau yx, the plane is in the at constant y, plane is constant y because of motion in the y direction. Plane is perpendicular to the y-axis, top face and the bottom face. It has an area of delta x delta z at y, delta x delta z, tau x at y plus delta y. Tau zx, molecular motion is in the z direction. Plane is perpendicular to the z-axis. Perpendicular to the z-axis is the front face and the back face. Area of the front face and back face is delta x delta y at z and delta x delta y at z plus delta x. Right? These are straightforward. We have been talking about this all the while. Now imagine that door thing again. We are trying to come into this box or go out of this box. Okay. Only way we will be able to come in is because of Vy, because of area, because of velocity component perpendicular to the door. We are writing force balance in the x direction. So we are only going to consider momentum per unit volume in the x direction. That's rho Vx. Rho Vx. This momentum will enter into this box because of velocity in the x direction through the left face. It will leave because of velocity in the x direction through the right face. Imagine that there is a train like this. Let's say this is our x direction. This is our y direction. You are there running in the x direction. Train is also going in the x direction. Train stationary if you want, doesn't matter. Right? You will be able to enter the train only if you have a velocity component in the y direction, perpendicular. How much momentum you are going to bring in is volumetric flow rate multiplied by rho Vx. So we have been talking about momentum is rho V and the rate at which it is brought in or out is rho v multiplied by q. Rho v multiplied by q, recall. Okay. So that flow rate could be because of Vx, Vy, Vz. Now we have done that in our continuity equation. Flow rates coming in and going out. So this you should be able to very clearly understand for yourself. Vx multiplied by delta y delta z through the left phase, out volumetric flow rate through the left phase, volumetric flow rate through the right phase. Vy delta x delta z volumetric flow rate through the bottom phase. Vy delta x delta z volumetric flow rate through the top phase. Vz delta x delta y volumetric flow rate through the back phase. Vz delta x delta y volumetric flow rate through the front phase. Okay. So all these forces we have to add up. The net difference is the accumulation of momentum, but that momentum is in x direction. So accumulation is mass multiplied by velocity in the x direction. Rho delta x delta y delta z, that's mass, multiplied by Vx, that's the accumulation of momentum with respect to time derivative. Right? Do this yourself. Make sure that you are able to understand all the things that that are written here. Divide throughout by delta x delta y delta z. Take the limit as delta x delta y delta z tending to 0. Okay. Do this yourself. Pause the video. Only when you have got it, go forward. Only when you get the final differential equation. Here is the final differential equation. In the x direction, you will have del rho by del of rho Vx by del t minus del by del x of rho Vx del by del y of rho Vy Vx, del by del z of rho Vz Vx. You will have minus del by del x of tau xx. Now we had written sigma there. So sigma now I had written sigma and tau just to differentiate between shear and normal stresses. Now that you are fairly comfortable, we don't have to write sigma, we can straight away write tau xx. This is normal stress. It's the same as sigma we had written earlier. Compression and elongation of stress. Tau ix, del by del y of tau ix, del by del z of tau zx, minus del p by del x, plus rho gx, that's the x component that we have. Similarly, we can write in y and z direction. What you should do is derive the force balance for yourself in the y direction and z direction by writing all these terms. Only when you do that, things will be clear to you. Do that for yourself. Write it in the y direction, write it in the z direction, all the balance that we have written like this, and get this equation. Get this equation for yourself. Let's go forward. Okay. If density is constant, equation of continuity gives you del Vx by del x plus del Vy by del y plus del Vz by del z is equal to 0. Okay. That's what is equation of continuity. What I want you to do is you can expand this bracket, right? Take rho out, rho common, rho is out, constant density, rho is you can take out. This bracket you can expand. This bracket you can expand. This bracket you can expand and use this continuity equation. Okay. Now, if you use this, the definitions of tau ix, tau xy, tau for the x directional momentum, what you have to worry about is only tau ix and tau zx. Use this definition, use this definition, use this definition of tau xx. This is 0, del dot v is 0. That's from continuity. So this entire term will vanish. Again, you can expand this, you can replace these tau definitions here. You can replace these tau definitions here and here and here. Again, use continuity equation, expand them as a bracket, use this continuity equation and simplify. See what you get. Pause the video, do it for yourself. Only when you do it, then only go forward. Okay. Here is what you will get. right? Here is what you will expand. Okay, use equation of continuity. I've just written it, but make sure that you get it for yourself. Here is what you will get. In the x direction, you will have rho del vx by del t, vx del vx by del x, vy del vx by del y, vz del vx by del z. Right hand side, mu del square vx by del x square, del square vx by del y square, del square vx by del z square. This is coming from tau xx, this is coming from tau yx, and this is coming from tau zx. That's the meaning of these. There will be minus del p del x and there will be rho gx. Okay? This is in the x direction. Same way we have to do for y direction and z direction. This equation and this equation. So you will get three equations because there is a force balance in all the three directions. So you'll have three equations. So now you see the beauty of writing things in a vector notation. We have all the three directions. This is one direction. Similarly, we have y direction. Similarly, we will have z direction. But if I write it in the vector notation, velocity is a vector, operator is a vector. I can write this either in terms of one kind of vector notation. We can write is like this: del vi by del t. So I is x, and j is a direction. Again, three directions: x, y, z. But there is a same direction here, and it's an addition over the three directions. So it is vj del vi by del xj, meaning it is vx del vx by del x, vy del vx by del y, vz del vx by del z. These three terms. Same way here, it is del square vi by del x j square. J is x, y, and z. So mu del square vx by del x square, del square vx by del y square, del square vx by del z square. These three terms. That is for the x directional equation of motion. Take I is equal to y, you will get the equation of motion in the y direction. This is called as equation of motion. Did I write that somewhere? Yeah, these are called as equation of motion. We write that somewhere. Yeah, so I have written it, equation of motion. Let's take I equal to z direction. Rho del vz by del t, Vx del Vz by del x, Vy del Vz by del y, Vz del Vz by del z, minus del P by del z, rho Gz, mu del square Vz by del x square, del square Vz by del y square, del square Vz by del z square. Or if you like, in the vector notation using these operators, you can say rho del V by del t plus V dot del V, V dot del, that's the operator, V dot del, V dot del, V dot del. It is like the dot product of V with del, divergence, V dot del, that operating on this V, minus del P rho Gi mu del square Vi. Del square Vi is del dot del. It is a dot product of del. Del square is del dot del. Dot product of this del with itself, del by del x, del by del x, del by del y, del by del y, del by del z, del by del z. So appendix B5 gives the equation of motion in terms of these stresses. Appendix B6 gives the equation of motion for a Newtonian constant density fluid. So for a Newtonian and a constant density fluid, these are called as Navier-Stokes equation. Why Newtonian? Is because we have used the stress definition, stress strain relationships for a Newtonian fluid. We have taken density constant. That is what allowed us to use equation of continuity and bring this rho outside. So this equation is valid only for a constant density and a Newtonian fluid. and that is called as a Navier-Stokes equation. Equation of motion for a Newtonian constant density fluid. These are called as Navier-Stokes equation. You can see appendix B6 of Transport Phenomena by Bird, Stewart, Lightfoot. Okay. Just to tell you the physical significance, maybe these equations are there. Yeah, so these equations are here. Appendix B6 in the Cartesian coordinate system, in the cylindrical coordinate system. You see del P minus del P, mu del square V, rho G, and this capital D by dt is like these terms. It is because of this is the capital D by dt. Rather than writing it in the short form, capital D by dt. Right, so capital dV by dt is same as del V by del T plus V dot del V. Why? Because this is called as a material derivative. It is as if you were sitting on the fluid, if you were a part of the fluid, what changes you will see. That is what is described by here. Let's not worry about that just now. Okay? But that's it's a short way of writing things. Let me write this properly. Yeah. Okay. Let's go back a little bit just to see the physical significance. Remember where this term has come from, where each term has come from. This term has come from accumulation. It has come from here. Accumulation. This term, where it has come from? It has come from here. It has come from here. It is because of convection. It is because of the flow coming in, going out. So it is called as convective transfer of momentum or convective transport of moment. Del P by del Xi is like pressure gradient, like a pipe. Let's say del P by del Z. Pipe pressure is P1 here, P2 here. It is varying in the Z direction. That's the meaning of this pressure force. That pressure force can be generation of momentum. Because I have applied pressure in the pipe, momentum is created, fluid starts moving. So it's a source of momentum. Same way rho gi, gravity. Gravity can be, there can be a liquid at a higher level, there can be an outlet at the lower level. Flow is because of the gravity. This rho gi is a force which is causing the flow. It's a source of momentum. It is arising out of the volume multiplied by density into g. It's called as a body force. It is a source of momentum. Where this term comes from? This term has come from stresses. It has come from here, viscous stresses. Right. So this represents viscous transport of momentum. Viscous stresses, viscous transport of momentum. Just to give you an analogy with heat transfer, imagine that there is a fire here. Hot air comes out of that and we feel warm because of that hot air. So we say it is convective heat transfer from that source to us. If I put a rod here, rod will conduct heat. It is conduction and radiation. Now for momentum transfer there is no equivalent radiation, so let's leave out this right now. Conduction is because of molecular motion. Molecules of this rod are vibrating, heating each other, transferring thermal energy, and finally that thermal energy is being transferred from one end to the other end because of temperature gradient. So it is because of molecular motions. So this is like molecular motion. Convection, hot air comes on our face, hot air comes on our body. So we feel hot because of velocities, because of bulk motion. Fan is throwing velocities, fan is throwing air at us. Bulk motion. It's called as convection. So this is convective transport of momentum. Okay? These are sources of momentum. accumulation. We could have accumulation of heat. This temperature in the rod will increase with respect to time. Temperature, we have started the fire at t equal to 0, somewhere after t equal to 20 seconds, 20 minutes or 1 hour, temperature is different, accumulation of heat. Same way momentum, it is easier to visualize for heat, it is very complicated to visualize for momentum. Do that for yourself, do that. You should be able to physically visualize all these terms. Okay. Visualize for yourself, pause the video until you are able to visualize. Don't go forward, let it take time. These concepts are very important, they are the backbone of what we are going to do, and therefore it is very essential to get them clarified. So clarify for yourself, understand for yourself. Unless you have understood yourself, don't go forward. Let's try to go a little bit further into this equation. Let's try to think a little bit further into this equation, what this equation means. Okay, this is that equation. Now, just to give you an example, just to give you an analogy, suppose we are trying to compare two things. Okay. Let's say we are trying to compare price of banana and price of, let's say, apple. Let's say banana costs 2 rupees per piece and apple costs 20 rupees per piece. So if I say, what is the relative importance? What is the relative cost of the apple with respect to banana? It is 20 divided by 2. Cost of one apple divided by cost of one banana. So when I'm comparing the costs of apple and banana, I have to compare cost of one banana and cost of one apple. The ratio of the cost of one unit will tell you what is the relative importance or what is the relative cost of one over the other. Okay. Let's think about this in terms of momentum transfer. Let's think about this in terms of momentum transfer. Imagine what we are saying. 20 rupees for one apple. ₹2 one banana. So if I have to compare relative costs, I am going to compare these. Apple is 10 times costlier than banana. Provided I am comparing one unit. Same way now, these equations, if I make them dimensionless and make all the variables go from 0 to 1, or at least of the order 0 to 1, then I can compare the relative importance of each term. So imagine we are doing this for a pipe flow, right? Pipe flow velocity profile is like this. We don't know that yet, we will derive that. But let's say average velocity is somewhere here, V average. We have seen V average is half of V max. And D is the diameter. So if I make length, if I have to apply equation of continuity, equation of motion for this pipe flow, I can make all the length dimensions x, y and z, make them dimensionless by this d, diameter of the pipe. Then everywhere it will go from either 0 to 1. I can make all the velocity scales dimensionless by v average. It will go from 0 to 1, 0 to 2 in this particular case, but okay, at least it's of the order of 1. If I make pressure dimensionless by the inlet pressure, let's say P0 is the inlet pressure, then everywhere the pressure values, dimensionless pressure values made dimensionless with respect to P0 will have a value between 0 to 1. So I am going to define dimensionless variables V bar as V divided by V average, X dimensionless X bar as X by D, P dimensionless P bar as P by P naught. Put that here. So this Vi, if I multiply and divide by V average, I will get it as Vi bar multiplied by V average. This Vj, if I make it dimensionless, I will get Vj bar multiplied by V average. This Vi, if I make it dimensionless, I will get Vi bar multiplied by V average. And that V average square we are going to take out common. So we'll have to divide by V average here. X distance we have to make dimensionless by making it into X bar. I will get a D in the denominator, which I will take common. I will get this D. I will have to multiply it by D here. So I will have a term rho V average square D outside. These variables now are made dimensionless, which means they are going to vary from 0 to 1, or at least they are of the order 1. Of the order means they are around 1. Okay. Similarly, pressure we make dimensionless. We will make it P bar and multiply by P naught. Length dimension, X dimension, make it X bar multiplied by D. Gi we are not going to do anything. Mu and we are not going to do anything. This Vi we are going to make it as, write it as Vi bar multiplied by V average. That V average I can take it outside. Dxj square. Remember this is dx twice. I will have to make it dxj bar square and d square outside. Okay. So get this equation for yourself. Pause the video, make this equation, get it for yourself. Only then go forward. Get this equation for yourself. Now, this term is of the order 1. This term is of the order 1. Of the order which 1 means it is varying from 0 to 1. This term is of the order 1. They are all of the order 1. O means of the order 1. Means varying from 0 to 1, if you like. So the relative importance of each of these terms I will get to know if I compare their coefficients like this. 20 is the cost of one apple, 2 is the cost of one banana. It's like coefficient. Or if you like, and write, if you want to write an equation, 2 times cost of one apple is equal to 20 times cost of one banana. One banana, P I'm just writing. So if you say cost of one apple is X, equation would be 2X would be 20Y. And if I say X and Y are 1 apple, cost of one apple, cost of one banana, then this ratio tells me the relative importance of cost of one apple with respect to cost of one banana. That's what we have here. I have to compare the relative importance. I have to compare the coefficients. This coefficient, this coefficient, this coefficient, and this coefficient. The way we do that is you multiply it throughout by D and divide throughout by rho V average square. Okay, you will get this equation. Multiply throughout by D and divide throughout by rho V average square. You will get this equation. Now look at this term. Does this look familiar? Yes, it is 1 by Reynolds number. This coefficient, what does it tell you? Relative importance of viscous transport divided by relative importance of convective transport. We have divided by rho V average square. That's where it has come from. That's where this has come from. We have divided by rho V average square. So this term tells you relative importance of viscous transport to convective transport, which means 1 by Reynolds number is a measure of viscous transport to convective transport, which means Reynolds number is a measure of convective transport divided by viscous transport. That's why we say that if Reynolds number is very small, that means convective 1 by Reynolds number is very large, viscous transport is important. Convective transport is not important. In terms of this equation now, if Reynolds number is small, this term would be significant, this term would be negligible. I can even drop it out of the equation. It will not change anything because it is insignificant in the equation. In the next class, we will actually see examples where we do that. 1 by Froude number is this term, dGi by V average square. It's called as a Froude number, 1 by Froude number. So Froude number is V average square divided by dGi. It tells you the relative importance of gravitational term divided by the convective transport. We have divided by rho V average square, convective transport. So Froude number is a ratio of convective transport to gravitational force. We had that Froude number when we were talking about piping. P naught divided by V average square, we call that as 1 by Euler number, or Euler number is rho V average square divided by P naught. Meaning of Euler number is convective transport divided by pressure force, or 1 by Euler number is meaning of pressure force divided by convective transport. So if you are talking about, let's say, a couple of places where this is useful. So if you are talking about flows in an ocean, gravitational forces are important. Right? Froude number is very important. If you are talking about flows where pressure forces are important, say atmospheric flows, because of pressure difference, flow of air happens. So there Euler number is important, viscous forces are not important, Reynolds numbers are large, viscous forces are not important. Right? Therefore this term we can neglect. So it allows us to simplify equation of motion. So then it becomes a simplified version of this equation which we can solve. That's the importance of these dimensionless numbers. Dimensionless numbers tell us what is the important term, which is the important term. So in laminar flow, our Reynolds number is small, creeping flow around a sphere. This is not important. Convection is not important. Only important is viscous forces. So whenever there is a laminar flow, we can safely neglect this term. For atmospheric weather people, atmospheric scientists, flows are large, caused by pressure, gravitational force is there, large heights they are talking about, they have to worry about. Viscous forces are not important because it's not layer-like motion. Reynolds number is large, so they will neglect this term when they are solving for weather, when they are trying to predict weather, trying to solve equation and try to see what happens to the weather. They will neglect this term. So different people, when you talk to them, when you ask them different, what is the Navier-Stokes equation, they will just give you different versions of this equation. Chemical engineers are the only species which deal with all situations: high Reynolds number, low Reynolds number, high Froude number, low Froude number, high Euler number, low Euler number. They are the only species in the world that deal with the Navier-Stokes equation in its full entirety. So doing chemical engineering, you can, everything else will become a simplified version because you can drop out some terms, either convective term, either viscous term, pressure term, gravity term, and so on. So doing chemical engineering, you can do any other branch as well. So think about all this. So just to give you, these are the Navier-Stokes equation in Cartesian coordinate system, cylindrical coordinate system, and we'll start using all of them in the next lecture. What we have done so far is from Transport Phenomena book, Bird, Stewart and Lightfoot, second edition. We are doing chapter 3, sections 3.1 and 3.2. Appendix B4, B5, B6 gives you those equations. And if you like, from White's book, we are on chapter 4, sections 4.1 to 4.4. That's what we have done in this lecture. So these last two lectures are the backbone of what we are going to do for the next several lectures. Make sure that the concepts that we talked about in these last two lectures are very, very clear to you. Okay? To derive all these equations yourself, visualize all these equations yourself. Visualize. Only when you visualize these equations for yourself, then only you will get an understanding, right? To help you further understand, we are going to solve problems in the next couple of classes, okay, for Newtonian fluids as well as non-Newtonian fluids. So let's stop here for this lecture.